into your office and saying, passing your
That's right.
someday, you're not here.
Yeah, that's right. If my son does anything with markers in his adult life, I'm going to go into his shop and switch them all around.
Well, it's even more evil is instead of changing the caps, would be to change the actual, like, the labels on the outside.
Ooh, yeah, or
That would take more work, but it would definitely be
or like swap out all their markers for like scented markers. That would be like the most.
Oh, that would be good.
Yeah. Oh, okay. So let's see here. Before I regret not doing anything today, let me go on. So we are to section 2.4, which is on the absolute value of an integrable function. Yeah. And not just that, Audric, in HD. Now we're in HD. Is it exciting? I don't know if it really matters or not. I may go back to SD because it's like a lot more data. But if it helps you, I'll keep it HD. So the theorem 2.4.1 says this: if f is in L1R, what would that mean? That's the Lebesgue integrable functions, right? And f is represented by this series of step functions, right? Then the absolute value of f is an element of L1 of R, and we have the following estimate. We have that the absolute value of the integral of f, all right, is less than or equal to the integral of the absolute value function of f, which is less than or equal to the series of the integrals of the absolute values of the component functions representing f. All right. I'm going to skip the proof of this. Okay. I think the proof is similar to ones we've already done. It is, of course, interesting. It involves a sneaky addition of zeros. I would also warn that I think the meaning of the big Z is changed from the last section of this section. Now big Z means all points for which the series like converges, whereas I think in the last section it was the opposite. And then there's corollary 2.42. It says that if f and g are Lebesgue integrable, then the minimum of fg and the maximum of fg are Lebesgue integrable. This I will actually look at the proof of because it's a line. Okay, so, and also I just wanted to talk about these formulas a little bit because they're, I don't think I knew that these were formulas. There's a formula for min and max. Did you know that? Like he's just like, the proof essentially rests on these two formulas. So here's the formula for min. Min, the formula for min. I used to have a student named Min. That's why it's funny to me. His name was Min Win. I always wanted him to write a paper with max loss. Let's see here. Someday that dream will be realized. I must find that max loss student and then pay them money to work together to make my dream of this happen. So like, I think this is to be understood point-wise. I think this is supposed to be understood point-wise, right? Like, if you calculate the minimum of f of x and g of x, right? That's 1/2 f of x plus g of x minus the absolute value of f of x minus g of x. So just start thinking through the possibilities and see how that works out, right? Like, let's just think about this formula for a second. what happens if, for instance, f of x is greater than g of x? What is wrong with me? Look at this. Golly. And I'm using this hideous Carolina blue marker too. Ugh. Sorry about that. So offensive. Then you notice then that this right here is positive, which means that essentially when this is the case, you erase these bars, right? You erase the bars and you're just left with f of x plus g of x minus f of x minus g of x. But so the f of x be canceling, and you get g of x plus g of x, which is 2g of x divided by 2. So it just, this formula simplifies the g of x. So that's how that works. And if you think through it with the other case, right, if you had f of x less than g of x, then you'd have, like, I'll write it down in that case, you'd have 1/2 f of x plus g of x. And then what happens with absolute value? If you have f of x minus g of x, well, that's negative, right? So this is minus a minus parentheses f of x minus g of x. However you want to put the minus in there, but that's what happens, right? And then this half should be on the whole deal. Lost track of my parentheses, but anyway, you get the idea. And so in this case, we get 3 minuses. So these guys cancel, and you're just left with, 2f of x over 2, which of course is f of x, right? So that formula really does work to be the min. And there's a similar formula for max, right? The formula for max is what? I'll write it up here. Max. I think actually, if you look at this min formula, we probably could figure out the max formula, right? Without even looking at the book. I think surely it's got to be plus the absolute value of f minus g, right? Does that work out? Because that's going to promote the opposite cancellation, right? Like when f of x is less than g of x, then this just becomes g minus f. So you get f minus g plus g minus f. And so the f's cancel, and you'd have, well, I've lost track of where I started, but I think that's the formula for max. I'll peek at the notes here. Yeah, that's the formula. Okay, so these formulas are understood pointwise. What do they mean? Yeah, I mean, granted, but in terms of the corollary we're trying to prove at the moment, can you see why those are helpful?
Okay, so we're using it to use another definition that we don't want.
Right, so we just, basically we have this identity, right? The integral of the min is what? It's equal to 1/2 the integral of, f plus g minus the absolute value of f minus g, right? So then what? Well, I think we have, let's see here, like, if I could actually remember all the results we've already gone over, we'd be in good condition, maybe,
Well, I guess you could just say, like, consider cases if f is greater than g. Well, no, it's for all except
well, let's see here. I mean, I suppose we have that the integral of f minus g, right? The absolute value of that, right? Is less than or equal to the integral of the absolute value of f minus g. I don't know if that helps or not. I don't know, I think I'm overcomplicating this. The basic point is that we're assuming that the integral of f and the integral of g, separately exist, right? So we could say that this is, 1/2 integral of f plus 1/2 integral of g minus the integral of the absolute value of f minus g, provided what? If we knew what? Provided this exists, right? So if you can prove that the integral of the absolute value of f minus g exists, given the data that we have, then we're good to go. And I think that was done already in like the last section, perhaps. Let me just take a gander back here at section 2.3. Well, we had preservation of inequalities. We might have to actually go back further even. I don't know, maybe. Huh. Well, maybe theorem 2.22. I guess, well, I guess you can prove that that integral exists given the data here. Man, I don't want to get into all that. Rats. You have any ideas, Audric?
On how to show that.
How to show that the integral of the absolute value of f minus g exists?
Good.
Yeah, given that f and g are, Lebesgue integrable.
Well, I didn't see where you started to try to use theorem 2.34, because that was the first one it said.
Oh.
And so, theorem
2. What is?
4 states that that L1's a vector space, and really we're just trying to say if you have f and g and f greater than g, f less than g, the integral of f is less than g.
Oh, but there you go. That's all we need.
Yeah.
Just what you said. But theorem 2.34 says L1R is vector space. Right. If L1 is a vector space, then of course f and g in L1R implies what? That f minus g is an element of L1R, right? And if that's the case, then we also know that by this theorem 2.41, that the absolute value then of f minus g is again in L1R, right?
Yep.
So, and then given all that, we can use linearity of the Lebesgue integral and not only have that the integral of the min exists, but in fact here's the formula for it. So yeah. And the proof for max is similar, okay? So, all right, so that's that. Thanks, Audric. I'm about to see, because I had a sense of dread. I had a feeling like I'm about to reinvent the wheel on my proof here. And indeed, I was right, because to do that would have been to reprove the fact L1R is a vector space, right? Now, theorem 2.43, which I'll write up here. I don't, I'll talk about that in just a second. I'm not sure. So this one is if L is, if F is Lebesgue integrable, then the, look at this. Then the limit as z goes to 0 of the integral of the absolute value of the translation of f by z minus f is equal to 0. All right, so there's that. Let's see here, the paragraph you're mentioning. So he says, yeah, that's a technical point. He says, integrability of f the integrability of this does not imply the integral of f exists, right? So we've been going the other direction, but he admits that we don't have the technology. Well, he says a little bit more than that. He says it's not possible to actually concretely construct an example. And basically all we can do is prove such a function exists. And he says the proof of existence requires mathematical tools not introduced in this book. You should look at the books of Real Analysis or Measure Theory, for example, Friedman, 1982, or Halmos, 1974. I'm not sure which Friedman that is. I think there are many.
Yeah, the Friedman I'm talking about is the one who, I might be wrong, but I'm pretty sure the one I'm talking about is the one that discovered exotic four manifolds.
Exotic four manifolds? Ooh, yeah, I don't know. I tend to doubt it, because that would have been like it seems like he would have been an analyst if he wrote such a book as this, but yeah, I will say that, I mean, people who do exotic four manifolds could be analysts. I mean, push come to shove, some of those things are, I mean, that is the cutting edge of analysis, some of those things. Like, this was one of the things that, well, I was just talking about Min. Min was telling me that it kind of, one of his, experiences maturing as a math student was coming to the understanding that, oh, real manifold theory is analysis at some point. It's not just linear algebra. If you watch me do manifold theory long enough, you'll start to realize everything I show you is linear algebra. Pretty much. Because the push comes to shove with analysis is, by and large, not something I should be doing in an undergraduate course. And there's there is no shortage of interesting linear algebra to share with you guys, right? Like, I haven't shown you all of it. Okay.
Go up to that chair if you want to use other boards.
What's that?
Go up to the chair.
I'm debating whether or not I need these. I don't think I think these are intuitive enough that we'll be able to. I think I'm just going to go on here. So we're now in section 2.5. Section 2.5, and I will get straight to the point here. The interesting part of section 2.5 is on series of integrable functions. And he claims that basically the result is that if you bump up the definition of, well, I mean, let me just state it here. Let f be a real valued function. All right. Real valued function and fn sequence of integrable functions. So you notice the difference there? Before, what did we take? A sequence of what? We looked at a sequence of what? Of what? What were the things in the sequence though? What kind of functions were they?
Sets of integral and absolute value of the terms convergent to a integral.
So the thing is, we used step functions before. Step functions. I'm not saying that these have to be step functions now. I'm merely saying that they're integrable functions, which means what? There is only Lebesgue integrable. So this means, in fact, technically, that those are represented by a series of step functions. All right? So we're replacing a series of step functions with a series of integrable functions, which if you want to put all things, if you want to put all your eggs in one basket, it's a series of series. Or if you want to look at it from a different perspective, we're kind of doing the big boy version of a linear combination of linear combinations. What do you remember from linear algebra? What's a linear combination of linear combinations?
I guess the weight should be coefficients and the factors should be linear combinations.
Right, but if, at the end of the day, what is a linear combination of linear combinations? It's very unexciting what I'm about to say. It is, again, a linear combination. And something happens here the same. So, in other words, if you, I mean, but it's not a finite combination here, right? We're taking a series. Well, let me just finish writing and then I'll start blathering again. For x element of R, such that what? The series n equals 1 to infinity of the value of fn of x is less than infinity. Then, right, f is represented by, let's say, f1 plus f2 plus dot 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 dot, which is also, we could write representing the sum n equals 1 to infinity of fn. So this is what we mean by, well, we're extending our definition of representing a function by a series of other functions to include the potentiality that we're looking at in a series of step functions, but now a series of integrable functions. Right. That's the thing. Each one of these f sub n's can be written as a sum of, let's say, g sub nk's, where the g sub nk's are step functions.
Oh.
And let me look at the proof of one of the things that follows. You'll see it there. Okay. I don't think it comes up in this next one. So, well, maybe it's in here. I don't know. That we got this lemma.
Each f sub n is itself a series of step functions.
Yeah, each f sub n, exactly. Each f sub n is in principle a series of step functions. And so here's lemma 2.52. I'm not sure I want to do this one because it's kind of lengthy. And I'm looking for one that's, a little bit shorter to write and that we can still see the idea in. This may not be the best one for that, but I want to state it anyway. So let f be Lebesgue integrable, then for every epsilon greater than 0, there exists a sequence of step functions fn such that f is represented by f1 plus f2 plus dot 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 dot, and the summation n equals 1 to infinity of the integrals of the absolute values of the steps is less than or equal to the integral of the absolute value of the function plus epsilon. He characterizes this as a technical lemma, which usually means it's not super interesting. But the proof is about a page long, and it well, it doesn't involve the kind of details that you were just thirsting for, Audric, so I'm going to skip it. Maybe this next one does, though. Okay. So theorem 2.53, it says if F is represented by F1 plus F2 plus da 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 da, where F1, F2, and so forth are integrable functions, then F is integrable. And the integral of F is equal to the integral of its components, summed added together. So this theorem right here makes good on my claim that see what is this? What is this actually saying? What's our definition of integrable function? But more at the base of it, though, it means what? That there exists a sequence of step functions, right? Which gives you back the function, and also that, like you said, the integrals of the absolute values of those step functions have to be suitably convergent.
So essentially, like, this is just saying that if you had Lebesgue integrable function, you can take linear combinations of them and integrate over that, because technically the underlying bit is step function.
Yeah, I think what this is saying is that if you add together a series of step functions, if you take a series where everything in your series is itself a series of step functions, again, you get a series of step functions.
See, I feel like this is not sound trivial, like, or is that why they made it a definition?
Right, but I mean, this is just notation.
Okay.
At this point, we have not said that F so constructed is in fact Lebesgue integrable. That's being said over there. That's the punchline. Then F is integrable if it's constructed as such. This is just notation. It's not. I mean, so let's look at the proof if I can try. I may regret it, but we will attempt to look at the proof here. So here's the proof by lemma 2.5.2. There exist step functions f and k, right? Such that, so, you know, the existence of step functions, there's always an existence of step functions. If you have a function which is, you know, Lebesgue integrable, there exists a sequence of step functions that adds together to give a function, right? But the reason this is a technical lemma is it's saying, not only can you do that, but you can set them up so that this happens, right? It added this little bell, you know, this little extra technical nuance to the series, and you know, just to make it, and that's going to be used over here. But anyway, so the lemma says that we can write Fn as being represented by Fn1 plus Fn2 plus dot 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 dot, right? Where these are step functions, right? And also, we can have the integral of the absolute value of Fn1 plus the integral of the absolute value of Fn2 plus dot 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 less than or equal to the integral of the absolute value of fn plus epsilon. But what epsilon are we going to pick? The same one we always pick for these kind of proofs, 2 to the minus n. Because of course, as you know, somehow a geometric series will appear. No, if we were to go into the full details, I'm sure it would. But anyway, yeah, so there's that. Does that make sense? So that's just, so that's the series of the absolute values of the steps, right?
Yeah, but these are all theorems we've already proved, like this all checks out.
Okay. But the difference here is that we're doing it, let's see here, what's the difference? I mean, we're doing this for a particular integrable function. Now, let's continue on here. And then he says, okay, so that's for all n in the natural numbers. And then he says, let Hn be sequence arranged from all the functions Gn comma k Oh, I think there's a typo here.
That's supposed to be a G, not an F.
I think that's a typo. Well, I guess it's not especially important, but well, it's just, yeah, make this an F is the quickest way. Listen, either you keep this GNK, right? And you switch all of these guys up here to G's, you know, or you leave it like it is. But I think, well, anyway, okay. So the point is, you have, why is it possible to do this? What are we looking at? We're looking at, I mean, there's something kind of